Hi, hello everybody. Welcome back to Anod Academy. So in today's session, we are going to learn about splitting of d orbitals in detail about the other geometries. Okay, so basically this is going to be a rank booster session, something that you will have to mug up. Okay, because all students won't be able to solve this, to be honest, to mark questions or answers from this particular topic, because the splitting of orbitals are not complete in any one of the references. So I have compiled all the geometrical, splitting patterns from Housecroft, Hughie, and I'm presenting it over here. So very important regarding improving your score, improving your rank, but then you'll have to mug up. Okay, you'll have to by heart the entire split. So let's start. We already know about the octahedral geometry, right? It is, so I'm not going to draw it again because already we know that the energy of T2G is less than EG, right? T2G orbitals are dxy, dxz, and dyz. And these orbitals are less than dx squared, y squared, dz squared, right? This is about the octahedral geometry. And when we talk about tetrahedral geometry as well, here E is less than T2. Now E corresponds to dx squared, y squared, which is equal to dz squared. Both of them are equal. So I have put comma in the earlier case. If that is confusing to you, you can put equal to as well. Okay, because they are degenerate. And that is less than dxz, dyz, and dxy, right? We know this as well. Also, we have learned about the square planar geometry. Square planar geometry. And we learned two cases, right? One is the case when you have 3D metals. So when you have 3D metal, the order is dxz is equal to dyz. Then comes dz squared, right? And then you have dxy, and at the top you have dx squared, y squared. This was the trend. When you have a square planar geometry, but corresponding to 3D metal. The same square planar geometry, if you consider it for 4D or 5D metals, then what do you have? Then we have dz square is the least. Then comes dxz, dyz, dxy, and dx square y square. So please note the differences. It's over here. We have spoken about this in detail in the previous video, so I'm not taking time to explain it again. All right. Now I'm going to talk about square planar, not square planar, square pyramidal geometry. Square pyramidal. You might get bored because you have to learn that trend and nothing much conceptual in this, but then do mark my words, you do get questions from here. I think trigonal bipyramid and all was asked for more than 2 times. Okay, in both GATE as well as CSIR exams independently, and you will be getting the same questions in other competitive exams as well. So the square pyramidal. What is square pyramidal? The geometry, how does it look like? You have a metal at the center. You have 4 ligands along the XY plane, square pyramidal, and then you have 1 ligand at the top. Okay, so in total, it will be like a pyramid facing upwards with 5 ligands. So this is how a square pyramidal geometry looks. And just in case you want to learn this, it is same as Z out elongation. It is just like Z out elongation. How does Z out elongation look like? If you have d orbitals, ideally in tetrahedral geometry, you have T2G and EG, right? Z out means Z components are elongated, energy is low. So you have dxz, dyz over here. dxy energy increased. Similarly over here, dz square energy decreased. And dx square y squared. This is how it is. So this follows the same trend. This follows the same trend. Okay, so the trend is dxz is equal to dyz, least followed by dxy, and then you have dz square and dx square y square. This is how the splitting of the orbitals happen in square pyramidal geometry. Now I have shown with respect to z out. Actually, the way it looks is no difference, but then I'm just saying, okay. The way it looks is dxz, dyz, and then you have dxy, dz squared, dx square y square. No difference, okay? No difference. I just showed this with respective to T2, G, EG, and Z out configuration because the splittings are the same. But then this is how you see in the references. That's all. This is the order. That's all that you have to know. This is the order of square pyramidal geometry. Let's write one example. Example is, let's say, NICN 5 times 3 minus adopts square pyramidal geometry. Now, if you look at the structure, please understand that you have both, please pay attention, you have both dz square and dx square y square along the axis, right? So we have two axial orbitals, we do know that. Among them dz square and dx square y square, both of them are axial orbitals. And the energy of dz squared is less than the energy of dx squared y squared, right? That means the repulsions of the metal ligand electrons are lesser along the z-axis than the xy axis, correct? That's why the energy drops. So if the electron-electron repulsions along the z-axis is lower, so which means electron-electron repulsions along z-axis is less than that of the xy plane. So if the electron-electron repulsions along the z-axis is lower, it means axial bonds would be longer. Axial bonds are longer than the equatorial bonds. I hope you understand the difference between the axial and the equatorial bonds. These are the axial bonds. So there's only one, ML. And all of them over here, these four, are the equatorial bonds. Now, how do we come to this conclusion that the axial bond is longer? Because this lies along the z-axis, whose energy is comparatively less. If the energy less, it means the electron-electron repulsions between M and the L along the z-axis is lesser. And that will happen only if their distances are huge. So ML bonds are longer than ML. ML axial bonds are longer than ML equatorial bonds, in case you get concept-based questions. Okay, axial bonds are longer. This is about square pyramidal. Next, you have trigonal pyramidal. Trigonal, bipyramidal, bipyramidal. How does it look? You have a metal, two axial bonds along the z-axis, and you have three equatorial bonds forming a triangle in the xy. This is how it looks. Trigonal bipyramidal geometry. All right. So a few examples if you want. Examples, and again, this has 5 ligands. So CuCl5 3 minus, CdCl5 3 minus, HgCl5 3 minus are a few examples. And the order over here is d orbitals are split into dxz, dyz, and then you have dx squared, y squared, dxy, and highest is dz squared. So see, this is how it is split. Or if you want to write the order which was asked, trigonal bipyramidal, a lot of times this is being asked, okay? That is dxz is equal to dyz, which is the least. Then comes x squared, y squared, and z square is the highest. Now over here, if they ask you to compare between the axial and the equatorial bonds. So how many axial bonds? 2 axial bonds along the z-axis. 3 equatorial bonds along the xy plane. Now let's look at the orbitals that lie along the axis. Who are they? dz square and dx square y square. Am I right? So the energy of dz square is larger than the energy of x square y square. If the energy has increased, it means the electron-electron repulsions along the z-axis is greater than the xy plane. If the electron-electron repulsions along the z-axis have been increased, yeah, that means the repulsions would increase only when they come closer. So the axial bonds are shorter. Axial bonds are shorter. I hope you're understanding. In the earlier case, we got the axial bonds to be longer. Here they are shorter. So actually, this is not the correct representation we are supposed to draw because the axial bonds are shorter. So let's try to draw them accordingly. So if we have a metal, axial bonds would be shorter and the equatorial bonds would be longer. This is how it is. Okay. This is the trigonal bipyramidal geometry. I hope by now you understand how to check the length. Hey, sorry. How are the ligands connected? The ligands are not. This is how it forms the geometry. A triangular plane along the x, and then you have 2 axial bonds which are shorter. Done. Next is pentagonal bipyramidal. Pentagonal. How will you learn all these? No way out, practice. No shortcuts, only practice. Keep on revising it. Nothing else can help you over here. Pentagonal bipyramidal. dxz, dyz of equal length. And here you have dx squared, y squared, and dxy. And at the top, you have dz squared. So can you see the trend is the same as that of trigonal bipyramidal? It's the same. The trends are the same. So you can mug it up, no problem. Got it. Trigonal bipyramidal as well as Pentagonal bipyramidal have got the same splitting, same as trigonal bipyramidal. And what is the other one that we learned? It was square pyramidal, whose splitting was same as Z out. So this is how you can learn, no way out. Okay, so that's done. Now the next one is square antiprismatic. Square antiprismatic. So actually you will have to rearrange the trigonal bipyramidal splitting. Let me draw it first. So here dz square comes the least. Okay. And then you have bxy, bx square, y square. And then at the highest, you have bx, z, y, z. So can you see? I'll just put them in the same screen. So here, dz square was the top, but in square antiprismatic, this comes to the bottom. So you can relate it like that. I'm not giving any hints. You can find out your own way and you can check. Here, this is at the bottom, and the next geometry, this has come to the top. Okay? So here the trend is dz square is the least, followed by dxy, dx squared y squared, and then you have dxz by z. Square antiprismatic. Next. Linear geometry. Linear. Complexes with linear geometry. Now please note down whatever we are writing. And with time, you will be able to practice. Again, I repeat, this is going to be a rank booster session because all students won't be able to learn this. So if you can, this is an added advantage if a question comes. You will be able to score. Okay, but then I understand the difficulty, you will have to learn. So this is for linear geometry. Then we have trigonal planar. Trigonal planar. What is trigonal planar? I'll write the order, okay? Dx squared, y squared is equal to dxy, which is greater than dz squared. And then you have dxz y plus. This is trigonal planar. And you have trigonal prismatic. Please, I understand with each geometry I write, you might feel very, 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 very pathetic, but understand that this is something which might help us to improve our rank. Dx square y square is equal to dxy, which is the least. Then comes dz square, and then comes dxz, dz. Can you see it's just the opposite? Here dx square y square has got the highest. Here dx square y square has got the least. Please note the sign, okay? This is this is decreasing. This has got the highest value. Here, this one has got the highest value. So please be careful with the signs. Trigonal planar we have written. Out of which trigonal bipyramidal has been asked again and again. Okay. And then there were two more geometry. Trigonal prismatic you can write same as ferrocene. You will be learning about this in organometallic compounds as well. But then you can just note it down over here that ferrocene has got the same splitting pattern as that of triangle prismatic. Ferrocene has not got a triangle prismatic geometry. It has got a standard structure, but the splitting patterns are the same. So you just note it down. When we learn the same in organometallics, it will be a revision. Okay. Next is trigonal prism. So understand that prismatic and prism are not the same. I'll just add them to square antiprismatic. So this is same as trigonal prism. Same. The trends are the same. Prism and prismatic are not the same. Okay. Trigonal prism is different. Trigonal prismatic is different. The structure of trigonal prism is same as square antiprismatic. Cubic, same as tetrahedral. Cubic structures have got same splitting as that of tetrahedral structures. That is E at the bottom and T2 at the top. Okay. Last one is dodecahedral. Dodecahedral. All right, which has got a splitting something like dz square is the least, and then dxy, dxz, dyz, dx squared y squared. Okay, this is how it is. Please be careful while you write these structures. Last one. There is one geometry called icosahedral. Icosahedral. Okay. Icosahedron, wherein the d orbitals won't split. If I'm not wrong, no questions have been asked from this particular stuff that we have written. So you might expect no d orbitals. D orbitals do not split because the ligands come in a uniform way. They're repelled equally from a uniform distance, and hence splitting does not happen. Okay. So yeah, that's it. Okay, so I hope I know there is nothing to understand over here. It's just about the length of the bonds that you have to note. Otherwise, it's completely mugging up. Octahedral, tetrahedral, square planar, T3D, 4D, Z out, Z in, and all, you are very comfortable now, I hope so. These, you try to find out some relation and try it on your own. I have already given some relations, like square pyramidal is same as Z out. Tetrahedral and cubic has got the same structures. Trigonal, bipyramidal, and pentagonal, bipyramidal are the same, which is say, which I've already written over here. Square antiprismatic and triangle prism are the same. Linear has got something else. All these you will have to relate and you'll have to, okay? It's actually easy if you revise it for a couple of times. Okay, so I'm winding up the session. We'll meet in the next. I think we'll be starting with ligand field theory. Okay, so see you.